So right here I've got a separable equation that I think is considerably challenging. I have that x over ln x dy equals root of y squared plus 4y plus 13 times dx. So already this is separating the variables isn't too difficult. If you follow along, you will end up with 1 over root of y squared plus 4y plus 13 dy, or you just put the dy in the numerator, minus x, or ln x over x, let me fix that there, minus ln x over x times dx, and that's equal to 0. So at this point you can go ahead and integrate everything straight across, and setting it up was the easier part. The integration I think is going to be a little bit more tricky. I'll go ahead and do this in yellow. So the easier of the two integrals that I'll tackle first is this ln x over x dx. So there's a simple u substitution. Hopefully it's just like screaming at you in the face, the function and its derivative. But u equals ln x, therefore du equals x to the minus 1 dx. dx is therefore x times du. So if u is ln x, then I'll write u instead of ln x. Here you have x in the denominator, and dx is x times du. So these x's get rid of each other, and you end up with the integral of u du, which is 1/2 times u squared. And normally I'd worry about the constant of integration, but in this case it's going to be on the other side anyway. So the integral of ln x over x is 0.5 times ln x squared. So this is the point where which we've gotten to, where the integral that we have to solve now is this integral of, in the numerator, dy, and in the denominator, y squared plus 4y plus 13. So let me scroll everything down here. So I'll take this to the side. I'll write it in yellow. So the integral of, let me get my pen out here. The integral of, not sure, oh, here. dy over y squared plus 4y plus 13. And hopefully, well, actually I encourage you to pause the video and try to tackle this yourself. So hopefully you had an attempt at it, and if I'm actually going to encourage you to pause the video and try to tackle this yourself again if maybe you didn't have any luck the first time. This time I'll leave it that it is a trig substitution problem, so pause the video and try to tackle this yourself. So hopefully after hearing the hint, if you needed it, that helped you solve this in the end, but if you couldn't, no worries. So the integral of dy over root of y squared plus 4y plus 13, and I already said this is a trig substitution problem, so we should probably be looking for a perfect square, or something that we can make into a triangle, the root of something squared plus something else squared. So this y squared plus 4y plus 13, this expression here, well, y plus 2 quantity squared, actually, so this is actually y plus 2 quantity squared plus 3 squared. See, by subtracting 9, you would end up with y squared plus 4y plus 4, and 9 is the difference between 4 and 13, and 9 is a perfect square, its root being 3. So this could all be simplified to y plus 2 quantity squared plus 3 squared, and then I can make a convenient triangle here. So let me make this triangle. So here my opposite side is y plus 2, my adjacent side is 3, and my hypotenuse is y plus 2 squared plus 3 squared. Hopefully that's neat enough. And this is my angle theta. So sine theta is y plus 2 over the root of y plus 2 squared plus 3 squared. So sine theta is y plus 2 over root of y plus 2 squared plus 3 squared. And actually, I'm not going to go ahead and write out every trig ratio. You should be able to do this yourself, but so upon writing out your 6 trig ratios, sine, cosine, tangent, cosecant, secant, and cotangent, and then taking your dy and translating it accordingly, and for starters, so tan theta is y plus 2 over 3. So y in terms of theta is tan theta minus 2/3. So dy is secant squared theta d theta. And so after translating the integral accordingly, this 1 over root of y squared plus 4y plus 13 with respect to y, that ends up being 1/3 times cosine theta and times 3 secant squared theta d theta. So the 1/3 and the 3 get rid of each other. The cosine reduces the secant by a power, and you end up with the integral of secant theta d theta. And that comes out to be ln secant theta plus tan theta. And so that actually comes out to be ln secant theta plus tan theta. After translating back from theta to y, that is ln y plus 2 quantity squared plus 3 squared plus y plus 2 over 3. So going back to the original problem now, let's rewrite all this. This integral was actually going with, I think, blue initially, so switch colors here. So going back to the original problem of 1 of y squared, or y plus 2 quantity squared, plus 3 squared, or plus 9, dy, or I'll just leave the dy in the numerator, plus, or minus the integral of ln x over x dx, and that's equal to the integral of 0, which is the constant of integration. So after having solved all of this, so the final answer yielded after having solved all of this is ln root of y plus 2 quantity squared plus 3 squared plus y plus 2 over 3 minus 0.5 ln x squared, and that's equal to the constant of integration. So at this point, if you wanted to get it in, say, x as a function of y, it'd be really hairy, and it'd really be a lot of work, or y as a function of x, that would also be a lot of work, or if not impossible, if you're talking about an implicit function, or an explicit function, I meant. So typically it is acceptable to leave solutions, especially if it's something like this, in an implicit form, in something of the form f of x y equals c.